Oh, it is the sixth attempt of the recording a video for a deep learning subject about diffusion models. I have prepared some bullet points about this topic, and I'm gonna briefly just explain what these models are, how they work, and just mention a few current trends with these models. Okay, so the first thing is actually the explanation for the models, like how they work, the underlying processes. So firstly, the diffusion models are used for image generation, and it is basically a substitute for GANs and I wouldn't say original autoencoders, but partially. So the first step in the diffusion generation process is basically adding a noise to some image. I will draw some stuff in here. Let's say like some smiley face. We have some smiley face. Then we are gradually adding some noise to this image. Like let's say this one is some noise, and at the end we are getting a pure Gaussian noise here. Yep, and it is usually made. It is usually made in one step. Here in one step, but this process can be separated into, like, let's say 1,000 steps or like 100 steps, and it can be described with this formula. Or I won't be writing any formulas here, but yeah, we have some notation. So x0 is the initial image, and here we have some a final basically image or the noise. T is the number of steps. In our case, we have like 100. It is, let's say, like 50. And yeah, that's basically how it's made, and it's made in one step, but it can be separated in like in T steps. And this T is basically, it's very important. It's used in the model itself. And regarding this T, we are using it actually during the denoising process, which is the second stage of the model's life cycle. So it is we are going back from a pure noise to the initial image. And now let me show you a formula for the training. So here's the formula, here's the loss. It is a simple mean square error. Yep, and epsilon is the noise that we are adding to the image during the step T. So okay, let me change the color real quick. Okay, it's not the color. Okay, highlighter will work. So here we use this T. T, as I mentioned, is the intermediate like step of adding noise. Epsilon is the noise, true ground truth noise that we were adding during the noising process, and epsilon theta is the model which is predicting the noise that we have added to the image. And for generation purposes, we simply can subtract this noise from the noisy image, and we will get like a less noisy or an image completely without noise. So that's how the model works briefly. If you're interested, you can watch some videos explaining how this formula is derived, how this is derived, but I won't be going deep into this. Okay. So now let's go to the interesting facts about these models. Okay, so the first fact is quite useful and quite interesting. In nowadays in the models, we are usually not adding noise to the images, but we actually firstly encode these images to some latent representation using a variational autoencoder. Okay, let me draw this two parts of the variational autoencoder. Here we go. So here we have some encoder and the decoder. So this image, okay. Firstly, this image, like again, it's my face is going to encoder. Then we are getting some. Let me move it a bit here. Then we are getting a latent representation of this image. It's basically it's undescribable. We can't describe it. But it has like, let's say, from 3 channels, we are getting like 16 channels here. So yeah, that's the latent representation, and of course we will have a smaller image, like if it was like 128 by 100. Okay, 128 by 128. We will get here like I don't know, 32 by 32 or 16 by 16. It doesn't matter, but yeah, it's the main benefit, one of the main benefits of this encoding process. So we don't need, we won't have like this huge image going to the diffusion model. I will draw this diffusion model here. Diffusion model. So yeah, that's basically the idea. And why we are using variational autoencoder for decoding images is that because this kind of encoder, it basically organizes the distribution of the latent space. So it won't be so random, so like scattered, and the diffusion models will be, it will be easier for diffusion models to work with such space, with such diffusion space. With such a distribution, not the diffusion space. So yeah, so yeah, that's basically the idea. And yeah, of course, in here, if usually we just put some noise, random noise to the diffusion model, and we are getting an image here, like a decoded image, of course, and we can encoded image, and we can decode this image using this diffusion. The diffusion decoder. We can use this decoder part of the variational autoencoder. And yeah, that's about the variational autoencoder. So we basically stack this diffusion model between an encoder and a decoder to firstly save some resources because these latent images will be a lot smaller than the initial ones. And the second thing is that we will have a more organized distribution for the diffusion model. All right, that's the one thing. So yeah, the second thing that we can have in the diffusion models is the external conditioning. And it's pretty fascinating thing. We can not only generate some random images with random noise, like we want to generate, for instance, a house or a dog, and we somehow need to tell the model what we want. So for that, we are inserting a special piece of data to the model. And it's usually represented as a vector, like it can be one hot encoded, for instance, 0, 0, 0. Yeah, like this. And this vector is then inserted into or integrated into this, as you can see, T. If you probably remember this T here or not. But in any case, this vector is firstly embedded. And then it is inserted into this this T. So it is basically fused together, and with such thing we can basically condition the diffusion model to generate not only some random image, but for instance a house that we tell the model to do so. Like if we insert a house encoding to the embedding to this part. Yeah, that's one thing. And also, just wanted to mention also that these embeddings can be anything. Like it can be not only like some text. It can not only be a class, but we can use, for instance, some pressed keys. For instance, if we want to generate frames for a game, we can pass some keyboard keys to the model, and it will generate us, for instance, a movement. If we press W, it will move forward. The image will generate a thing that is moving forward. So and so on. So yeah, it's a pretty interesting thing, and it is pretty flexible. Okay, it's the one thing, and the last thing that I want to talk about is the embeddings in the models. So we can not only embed our external condition, but it is also a usual practice to embed these images. So let's say we are having we have this some image. Let's say it's a Latin space representation of a smiley face. But yeah, and when we pass this image to the diffusion models, to the diffusion model, this model firstly creates an embedding of this latent space image. And it's called usually a patch embedding. So the image is separated into several blocks like this. And these different blocks, they will have like whatever, they will have like not 3, for instance, channels like as the initial image has, or like 16 as the latent image has, but it might have like 32 channels or like 8 channels. So each patch will have like 32 or 80 8 channels to represent a certain thing. Yeah, that's basically a part of a specific version of diffusion models called DIT. So it's a diffusion model transformers, which uses a principle of like a visual transformer, shortly it's VIT. And yeah, that's it about the embeddings. And yeah, of course, these latent space representations, they will make it easier to digest the data by transform. The digestion of the data will be easier, or the processing of the data will be easier for transformers, because we will have less of these patches. We will have more channels here, of course, but less patches. All right, that's it about. Okay, maybe one thing I'm now thinking. This representation of the embedded image, like in VIT we have here, it may be, it may have like this shape, like it may have like some width and some height and some width here, but it can also be a simple flat flat tensor that contains these patches of the image. So yeah, it depends on the model. For instance, some models may benefit from this representation, and some are better with this representation. So that's the thing. And I think that's it. I don't have anything on my list, so yeah. Thank you for your attention, and yeah, hope you enjoyed it. It was a bit chaotic. It was like unscripted, but yeah, hopefully it was enjoyable at least. Thank you.